Okay, welcome to this Science 10 review. It's going to go fast because it's review. You should also have your package that it goes along with this PowerPoint, and you can be highlighting, annotating notes, and participating in the practice examples as we go along. Actively engaging is going to help your mark increase. Okay, so first of all, you should know the periodic table was founded by Dmitry Mendeleev, a Russian. His table predated a lot of what we know about atoms, and so we didn't really know that they went in this order because of the number of protons, but that's what ended up happening. Now, the reason he got his name on as the founder of the periodic table is because he made some predictions. He said, I'm so confident about the properties of all of these and the properties of all of these. I bet I'm going to make up an element. This is the one, and I bet it's going to have these type of properties. And when that element was discovered, it did have those properties, and so he was famous for that. Okay, so they are listed in rows and periods. Periods and groups. The rows are periods. They run left to right. Period 1, period 2, period 3, period 4, period 5, etc. And then groups are in columns. So group 1, group 2, group 3. You can memorize that maybe because groups is the shorter name, and those are shorter in length. Then the period is a longer name, and therefore it's longer in length. Okay, so but you need to know if I say group 3, you need to know to look at up here. That would be this column right there. Okay, there are some important groups. Alkali metals are group 1, alkaline earth metals are group 2, halogens are all the way over here, the second last column. They are group 17. Halogens are quite important because we'll often say like a halide, and students are like, what's that? Okay, so that'll follow you into Chem 30 even. And then group 18 are your noble gases because they are very unreactive, and so they're noble. They used to be called inert, but we can get them to react a little bit now. So now they're called noble gases. When you look at the periodic table, you'll see a symbol, and you'll see some. Let's see if I can move my face here. I don't think I can. Sorry. You'll see a atomic number there with its symbol. You'll see a name down below, and then this number 12.011. Or 12.01 in your periodic table. We only have 2 decimal places. This is the atomic mass. Okay, so the atomic number, which for carbon is 6, it tells you that it has 6 protons. And if you notice, the periodic table is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there are no half a proton. The atomic, well, let me just put the whole screen up here. The atomic mass is how many grams a mole of atoms will be. Now remember, a mole from grade 10, a mole is a 6 billion trillion. So if I could take 6 billion trillion carbons and put them all together, that would weigh just 12 grams. So 12.011 grams would be 6 billion trillion atoms of carbon. We can use the atomic mass and the atomic number. We can subtract them and come up with the number of neutrons. So we're going to round this to the nearest whole number. 12 minus 6 is 6 neutrons for this carbon. In order to solve for the number of electrons, we can take the charge. So you have to think, is this neutral or is this charged? This one doesn't say it's charged, so it must be neutral. Therefore, it's an atom. Atoms are neutral. And in order to make it neutral, if I have 6 protons, I better have 6 electrons in order to balance it out and make it neutral. So that is how you tell how many protons, neutrons, and electrons. Right, so here's an example right out of your notes. Magnesium and magnesium ion. They are very different. They are named differently, and that little 2+ means something very different. So this magnesium, which is on your periodic table, by the way, print off the periodic table that was provided to you by your teacher. You want to become super familiar with that periodic table. Don't use last year's, don't use something you just found on the internet. Use what you're going to have on a test so you feel super comfortable about where to find everything, what the colors all mean, etc. So this is a screenshot from the periodic table that you should be using in Science 10 if you're in my class. And you can see here that magnesium, if it's neutral magnesium, a metal, because it's on the left-hand side of that staircase, that would mean that it has, ductile and malleable properties, sonorous, shiny metal, silver, etc. Okay, so that magnesium atom has an atomic number of 12. So it has 12 protons. It has an atomic mass of 24.31. That would be an average of all the isotopes that are in there. The most common then is 24. So I round that to the nearest whole number. So 24 minus 12 tells me it has 12 neutrons. Atoms are neutral, and therefore I need to have 12 electrons to balance out those protons and make it overall neutral. This is compared to something different, magnesium ion. Magnesium ions are not metal, they are ionic. In fact, I would find magnesium ions in foods that I eat because it's an ionic compound. If I had just a solid of it, then I would have like magnesium chloride, for example, and it would be a white powder, not a metal at all. So these ions, I can eat this one. These ions look very different. They act very different, even though in Science 10 on the periodic table, it feels the same. It's not the same. And it's very important that you put the correct thing down, otherwise you'll lose marks. So magnesium ion is what its name is. Mg2+ is its symbol. I get the 2+ because on this periodic table it has a little 2+ on the top, or because all of group 2 are 2+. The atomic number is still 12. It still has 12 protons. The atomic mass is still 24.31 because the mass doesn't change because electrons are so itty bitty. And then it has a charge of 2+. So in order to have a charge of 2+, I have to have 2 protons more than the electrons. But I can't change the protons. It has to stay at 12 because the atomic number is 12. So I have to change the electrons. I'm going to change the electrons to 10, and therefore overall my item is going to be a 2+ charge. Okay, let's flip on to the next slide. So oopsies, this is the one that is, I don't know how to go back, you guys. Hold on a minute. That was a focus on metals. Now we're going to have a focus on nonmetals, which are the blue ones on your periodic table. So we've said that they're on the right-hand side of the staircase. They tend to gain electrons and become negatively charged ions. When they are ions, they are negatively charged, and they are called anions. So anion for negative and cation for positive. Cats have paws, positive. Okay. With metals, they were more reactive as you move down, francium being the most reactive metal. And for nonmetals, they're more reactive as you move up. So fluorine is your most reactive nonmetal. We can't include the noble gases because they are not reactive, remember? Their properties, they can be solid or gas. They are dull, not shiny. They are brittle, meaning if I drop it, it crumbles into a million pieces. They are not very good conductors of electricity or heat, and they tend to have lower melting points and boiling points. Metalloids are those yellow ones. Metalloids are on the staircase, and they have properties of both. Okay, so Mendeleev, who we talked about as the father of the periodic table, noticed there were trends, and that's how he arranged the periodic table. Those trends still exist. So we're going to talk about some trends in valence electrons and polyatomic elements. We already talked about trends in reactivity, right? Going down for metals, going up for nonmetals. So here's a trend about valence electrons. Now in Chem Science 10, you hopefully did a bunch of Bohr diagrams. You're going to still do some Bohr diagrams for me in Chem 20. And you're going to have to draw these valence electrons. The valence electrons are the outermost electrons, so in the outside ring here. When you're determining how many valence electrons it should be, this is going to be in group 3 because it has 3 valence electrons. 3 or 13. So if you look up, there's the boron just there. If you look here, it's a group number 13. Ignore the 1, 3 valence electrons, 4 valence electrons, 5 valence electrons. Okay. And then your polyatomic elements are the ones that don't like to be by themselves. So we never have oxygen atom by itself in nature. We might in an example that I'm just asking you to draw the Bohr diagram for an oxygen atom, but the element of oxygen always comes paired up, O2, N2, H2. So a lot of them come in pairs, and then some of them come in a bigger group. So P4 and S8. Now, a lot of students memorize this a lot of different ways. A lot of teachers teach it in a lot of different ways. The way that I think works the best for students is to look at the 7-up method. So the special 7-up, first of all, you find the atomic number 7, that's nitrogen, and it makes a 7 on the periodic table. So nitrogen is N2, O2, F2, Cl2, etc. And then the special up part is this H2 that exists here. I worked for a hockey school once and we called it a hockey stick and a puck. Okay, all right. However you memorize it, you have to know it. So if I ask you for the symbol of magnesium, we're putting Mg down. Magnesium ion, we're putting Mg2+ down. And if I ask you for the symbol of fluorine, you're putting F2. You're not just putting F. 13. Oh, I did it again. Okay, not ironic, which is what this song is, but rather ionic compounds. How are you going to tell if it's an ionic compound? You're going to look for it starting with a metal or starting with an ion. That's how you know that it is ionic. So in Science 10, hopefully you were introduced to a better definition of an ionic compound, but maybe you weren't. In Chem 20, you absolutely 100% have to write this definition for an ionic compound. It is an electrostatic attraction, meaning they stick together like magnets. Electrostatic attraction between oppositely charged particles. So positive and a negative are attracted. That is the definition of an ionic compound. It is not about this transfer. It is not about this transfer. If I see the word transfer in your definition, you will lose marks because it is not necessarily a transfer. That's how you can create an ionic compound. But if I'm just digging some salt up in the earth, it's already an ionic compound. There is no transfer happening. It is already Na plus and Cl minus. They are attracted to each other. They are bonded to each other. They form a compound because the positive is attracted to the negative. So this is our new definition. Make sure you highlight it, memorize it, learn it. Remembering a cation is a positive ion and an anion is a negative ion. So an ionic compound is an attraction between the cation and an anion. Remembering that it's not just one sodium ion and one chloride ion, but rather it is a crystal lattice structure, so that lithium positive ion is surrounded by chloride ions. It is not a molecule. It's a formula unit, meaning the smallest ratio is represented, not the exact number of ions. So it's not, if I wrote down sodium chloride, it's not just one sodium and one chloride. It's a bajillion to a bajillion. It's a ratio that we're writing down there. When we are naming ionic compounds, we're going to write the metal first, sodium. We keep the name as the periodic table states, even though if we were by itself, we would write sodium ion. And then we're going to look up the next one, and we are going to change its ending to IDE. So instead of chlorine, which is what it's on the periodic table, we're going to have to write down chloride. Every ionic compound is made up of cation and anion because it has to. So those are the rules. We're going to practice those rules using these examples. They are in your package under this ionic compound naming section under We Try. So we're going to do these ones together, and then there's a handful more in there for you to practice on your own, and then an answer key to check your work. Okay, so when we are trying this calcium chloride, you're going to look up on your periodic table, which you have printed off and right beside you. You're going to look up Ca on the left-hand side, knowing that this is an ionic compound because it starts with something on the left-hand side of the periodic table. And we're going to find it, and then we're going to name it calcium, just like the periodic table. Don't change it. Then I look up this second thing, which is a nonmetal. So because we have something from both sides of the periodic table, this must be ionic. That's important to remember because when they're all mixed up, you have to know what to do. And so I look that up. It says chlorine, but I'm not going to write down chlorine. I'm going to change the ending to IDE. And so this is calcium chloride. Okay, following the next one. Again, we're starting with a metal, and so I know it's ionic, and I'm going to write down calcium again, just like I did before. So that hasn't changed. This part, though, is a little different. Here I have something that is called a polyatomic ion. So on your periodic table, right in the middle of the periodic table there, you'll see a table of polyatomic ions. It's in there. The O and H are bonded together, and together they make an anion. And that anion of, must be a Ca2 plus, and then you're going to look up on that, you're going to look up on that sheet there an OH minus, and that OH minus is called hydroxide. So calcium hydroxide, a cation and an anion. I needed 2 of these hydroxides in order to make it overall neutral, 2 negatives to balance out that 2 positive, which is why that little 2 is there. Okay, looking at the next one, I look up Li on the left-hand side of the periodic table, and it is lithium. Notice I don't have a capital on any of these. That kind of looks like a capital, so I'm actually going to redo it. Lithium. And then again, this big long thing here is something in your polyatomic ion table. So that Li1 plus is balanced out with the anion CH3COO. Now it's written like that because that tells you a little bit about its shape and structure, which we're going to learn later on in this unit. But for now, we're just naming. So just know that there's a reason I didn't schmuck the O's together or schmuck the C's together. It gives you an idea of its structure, its layout. And so if I write this name down, it is FNO8. So I just copy those ones from the polyatomic ions. I just copy them right like they are on the data sheet. Here we have Fe and Cl2. I look up what Fe is called, and it's called iron. And I look up my Cl, and it's chlorine, but I'm going to change the name to IDE, just like I did up here in question 1. Now, we need to add a little layer here, though. Because if you look at your periodic table, it tells you that iron can be multiple charges. So if it can be multiple charges, the name has to include which charge is this one. So if that chloride must be a Cl minus, and I have 2 of them, then that iron must be a 2 plus charge in order to make the compound neutral. So this is iron 2 chloride, so that the iron 2 plus and 2 chlorides balance out into a neutral compound, as opposed to an iron 3 chloride. If this was a 3 plus, that would not balance the compound out, right? If this was a 3 plus, then I have 2 negatives and 1 3 positive, and that doesn't balance out. Okay, here I look up all of these things, and they're all nonmetals, which leads me to think it's not ionic, except for I also notice that this is on the table of polyatomic ions, and this is on the table of polyatomic ions. So because they're both on the table of polyatomic ions, then what we have here is the cation, NH4+, and the anion, NO3-, making this ionic. So how do I name that cation? It's called ammonium. And how do I name that anion? It's called nitrate. And so the name of that compound, that ionic compound, is ammonium nitrate. Okay, there are a pile more for you to try, so I would pause this video right now and I would spend 10 minutes practicing those before you move on to the next section. Okay, so sometimes we talk about the charges balancing out like I did already. But other times we can use this crisscross or swap and drop, or however you want to call it, method. It's just a fast, easy way of making sure the charges are balanced. So, and some students really have a hard time knowing how to balance charges. So this is a nice, easy example. So if you look at, so this is about not naming because we did that, but rather taking a name and writing the symbols. So if you are writing the formula, you have to look up the charges. So if it was calcium oxide, you look up the charge of calcium, it's calcium 2+. You look up the charge of oxide, it's O2-. Notice on the Chem 20 data booklet, you will not have the charges for the O. You have to know that everyone in group 16 is going to have a -2 charge. So first of all, you should know they're negative. Second of all, you go with a 6 valence electrons for group 16, and 6 plus 2 makes 8. So 6 plus -2. So 2- for the oxygens. Group 17 would be 7 valence electrons, and 1 make 8. So all of group 17 are going to be 1-. All of group 16 are going to be 2-. All of group 15 are going to be 3-. Okay, so you figure out the charge. So I've got the charge of calcium ion, I've got the charge of oxide ion. They are a 1-to-1 ratio, so 1-to-1 ratio. I look up Pb4+, I look up O2-. I need 2 oxygens to balance out my Pb, so I have PbO2. If you're using this swap and drop method, we would take the 4 and bring it down here. That makes this 4 there. We would take this 2 and bring it down there. So this is the crisscross. Bring it down there and make Pb2. So then I have Pb2O4, but that's not the smallest ratio, so I have to break it down into its smallest ratio, which is 1 and 2, making what we would have had before. So this swap and drop method comes in handy when it's something like aluminum oxide. Aluminum is a 3+, oxygen is a 2-, which you look at the periodic table, group 16, they're all 2-, and aluminum is 3+. It states that it's 3+. And I'm going to take the 3 and I'm going to push it down to the oxygen. I'm going to take the 2 and I'm going to push it down to the aluminum, and therefore it's Al2O3. That is the fast method of doing it. It actually works really well if you're trying to figure out the charge on a multivalent. It's easy to see that this would have been iron 3+, because of that 3 there, as opposed to working back the charges of the ratios, the fact that I need 6 positives and 6 negatives. Okay, so these are also in your package. So about taking ions or taking a name and writing it. So these, this would be called iron 3 nitrate. You look at it and you've got an iron 3+, according to the, let me just get some colors going on here. You have an iron, come on, an iron 3+, and then you have a nitrate, which is on your polyatomic ion table, of an NO3-. This comes as a package deal. Please do not change it, ever. So I can't touch that. It comes as a package deal. Wrap it up in a package. I need 3 of these to balance out that Fe3+. So then therefore that's going to be, so I think the first line is you're supposed to write down those ions. Then we're going to put them together, and I'm going to write FeNO3. I need 3 of those packages, so they're in brackets. If I didn't put brackets there, it would look like 33. That would be a little weird to have 33 oxygens and 1 nitrogen. And then it asks you to name it. So the name here would be iron 3 because it's multivalent, so I need to have its charge, and then I just keep that name nitrate. Okay, what about aluminum and nitrate? Looking up on your periodic table, aluminum is a 3+, nitrate is the same as we just finished with. Again, I have to have 3 nitrates for 1 aluminum. And again, I need to put brackets around that. And then the name here, oops, aluminium. I do not need a Roman numeral, nitrate, because there's only 1 charge for aluminum. It's always 3+. Looking up sodium on my periodic table, it's in group 1, so it's a 1+. Sulfate, that tells me ATE tells me that it'll be on the polyatomic ion table. It will not be on the periodic table. Periodic tables are IDE. So if it was IDE, then it'd be just S. But because it's ATE, I'm going to look up the data of the the polyatomic ion table, and it's SO4 2-. So in order to make these balance, I need 2 of my Na pluses, and I need 1 of my SO4. That does not need to go into brackets because there's only 1 of them, so I don't need to wrap it. And then the name here would be sodium sulfate. Sulfate is pH or F, depending on whether you're talking about imperial names or US naming. Lead 4, so I swap because I used to live in England, so I do both. Lead 4 and sulfate. So lead 4 is a Pb4+, and a sulfate is an SO4 2-. I need 2 sulfates for every 1 lead 4+. So Pb, and then in brackets SO4 2, because I need 2 of those packages in order to balance out the lead 4. And then the name would be lead 4 sulfate. Okay, magnesium and carbonate. Magnesium 2+, carbonate CO3-, just a 1-. The 3 is subscript. And I need 2 of the carbonates. So again, can't touch this, so don't change that 3. And so I need 1 of the Mgs, and I need 2 of those CO3s. Then I put this one in because this is a weird one. It has 2 names, but actually it's only 1 thing on the package. So, and it's if you look at the polyatomic ion table, it's HCO3, can't touch this. So the zinc is a 2+, and this is my anion. I need 2 of those to balance the compound out. So Zn HCO3 package, 2 of them. And its name would be zinc hydrogen carbonate. Okay, great. That naming system, now you need to practice, so go ahead and try some more. If you need to find a YouTube video about this in order to help your understanding and just see somebody doing more of these, there are tons of great ones out there. Reach out to your teacher for some specific ones if you don't know what to watch in the sea of videos. Okay, molecular compounds. So ionic compounds are recognized because we would 1 from each side of the periodic table, cation and an anion. metal and a non-metal, but don't say that, don't write it. Molecular compounds have 2 non-metal atoms or more, 2 or more non-metal atoms. I just thought to myself, I probably haven't said to you why you can't write metal and a non-metal. Metals are neutral. Non-metals are neutral. Those are atoms. So I can't say neutral is an ionic compound. I have to say cation and anion make an ionic compound. But when you're looking at the periodic table, you're looking for something on the left hand where the metals are and the right hand where the non-metals are in order to figure out it's ionic. So molecular, they're all on that corner of non-metals. And so if you have all non-metals, then you don't have any ions. If you don't have any ions, it's going to be a molecular compound here. The definition of a molecular compound is that they have covalent bonds. So these words are interchangeable almost. Molecular compound, covalent compound, molecular bond, covalent bond. Molecular bond is not technically correct, but people use it. So what is the definition of a covalent bond that occurs in a molecule? It is a shared pair of electrons. So with an ionic compound, they stick together because positive and negatives attract. With a molecular compound, they're going to stick together because they need each other's electrons. So imagine if you were desperate for let's say you got lost in the forest and you had a power bar between you and your friend to share. You must share this power bar together. Do I mean power bar? I don't know, clip bar. I mean like that thing, protein bar, that's the word. So you're going to share this electron because you have to bond together in order to stay stable. Now, the naming system with rules is called an IUPAC naming system. So we learned about the IUPAC naming systems for ionic compounds. And then there are IUPAC rules for molecular compounds as well. However, some of these compounds were around before the rules came about. So they have common names, like water is not called dinitrogen monoxide, but rather it's just called water. So here are the formulas and here are the common names for ones that I need you to memorize. From here on in, you may not write down dihydride monoxide unless it specifically asks for the IUPAC name. You must write water. So that's very important for something like methane or ammonia. You will lose marks if you put that it's nitrogen trihydride. You must put that it's ammonia. So there are more common names, but these are the ones that I want you to memorize. These are the ones you'll be tested on. When we are naming the molecular compounds by the IUPAC name, we're first going to write the entire element of the first one. Then we're going to change the ending of the second one to IDE, and then we're going to tag on prefixes onto either name, the first and the second. Prefixes meaning mono, di, tri, etc. And we're going to omit the prefix of mono for the first one. So it's never mono nitrogen monoxide. It's just nitrogen monoxide. So you leave out the mono on the first one always, but the rest you would put on the first one. So let's pick one over here. Let's take this one. If I'm looking at N2O5, it's dinitrogen pentoxide because we have 5 oxygens. Now, what's weird about molecular compounds versus ionic compounds is that the numbering, this 2 goes with the oxygen, but the charge when they were ionic was the other way around. So students sometimes make a mistake on that one. So just remember that the number that comes after the atom comes before the word. So dinitrogen N2. See how that di comes after the N in the symbols, but in the words it comes first. Okay, so you have to have these memorized all the way up to 10, mono, di, tri, tetra, and then the rest is like math, penta, hexa, hepta, octa, nona, deca. So you probably will struggle with the tetra the most, which is number 4. Okay, so commit those to memory. And again, we're naming them all in lowercase. So let's do some of these examples here right out of your package. So if I'm taking these examples, and I am looking at the first one, diphosphorus pentaoxide. This means I have 2 of the phosphoruses, 2 of the phosphoruses. So I'm going to have a P for the phosphorus and 2, that's my diphosphorus, and then the penta for the oxides. So for the oxygens, I have 5 of them. Here I'm naming it. I have 2 of the nitrogens, so this is dinitrogen. We keep that naming the same. We do not change that naming. It stays the same. And then 1 oxygen, so this is monoxide. Here I have 3 of the nitrogens, so we have trinitrogen, 6 of the oxygens, so 6 was hex oxide. Here I have 2 of the hydrogens and 2 of the oxygens, but I'm not going to use di. I recognize this is one of the ones I need to memorize, and so I'm going to write down hydrogen peroxide because that's one I have to memorize. Okay, moving super fast into acids and bases. So just a quick little overview. First of all, bases are ionic compounds. So they're named like ionic compounds. They dissolve like ionic compounds, etc. How you know it's a base is it ends in hydroxide, which is an OH minus. That's the anion involved. So sodium hydroxide, potassium hydroxide, these are bases. And the symbols would be, well, just like we did for ionic compounds, that's the sodium ion, that's the hydroxide ion, and therefore putting them together, I get NaOH. Potassium hydroxide would be K plus and OH minus, so KOH. Acids are aqueous, and they're going to have an H plus to them. We learn a little bit more about acids this year, but for now they start with H plus and Cl minus, H plus and NO3 minus, etc. I want you to know hydrochloric acid is HCl, nitric acid is HNO3, and sulfuric acid is H2SO4. Please have those, there's a typo there, please have those memorized because they're going to come up again and again and again, and it is just faster if you have them memorized, H2SO4. Okay, you need to know about properties of acids and bases. So the property of a base is it feels slippery, like, you know, if you touched it, like soap. It tastes bitter. So for example, baking soda would taste bitter, toothpaste can taste bitter, and it turns red litmus paper blue. Look, tasting bitter is so important, it's on there twice. It has a pH of greater than 7. And then property of an acid. Is that they can be corrosive, sour, turn blue litmus paper red, and a pH of less than 7. So think of lemons for acids. Okay, where students seem to make the most mistakes is when everything is mixed up together. You got acids, bases, molecular, and ionic all on the same sheet. The key to success on these is to make sure that you think to yourself first, is it an acid? Is it ionic? Is it molecular? Then you can name it accordingly. So first of all, when I'm looking at this example here, I'm going to look to see that this says acid, therefore it is an acid, and it's one of the ones I'm supposed to memorize, HCl. So that's a lowercase l there. So that is something that you need to memorize. It's not one of the IUPAC names. And then the form, we would put an A here for the fact that it's an acid on that table that's in your worksheet. And also in your data booklet that you get, you will notice that there's a whole table of acids, but we want you to have those 3 memorized so that you're not looking through the whole table for all of them. So again, over here, I'm recognizing that that starts with an H, and therefore it's an acid as well, and it's also one I need to memorize, sulfuric acid. Okay. Now, CAS. When I look at this, it's not an acid because it doesn't start with H. I look up Ca on my periodic table and it's on the left-hand side with the metals. Therefore, this is ionic. So as soon as I determine that this is ionic, I then know how to name it. It's about charges. It's about changing the last name to IDE, and it's not about monos and dies. So as soon as I've decided that it is ionic, I'm going to name the calcium, which is a 2+, and the sulfide, pardon me, is an S2-. So this is going to be calcium sulfide. Okay, now when I look up the next one, P and O, it's not an acid because it doesn't start with an H, and so I look up the P and I notice that that P is not on the metal side. It's not over on the left-hand side, but rather it's on the right-hand side, making these non-metals. If they're non-metals, then that makes this molecular. If it's molecular, I'm going to use the dis and tris. So because it's molecular, this is going to be called diphosphorus. Do not change that ending. And then the pent oxide. Oops. We drop the A for the oxide. Okay, phosphorus pentoxide then. So you start, when you're naming these, you start with deciding what it is and then deciding, do I need Roman numerals? Do I need the dyes? Based on the fact that it is ionic or non-metal molecular. Okay, so go and practice a pile of these. Again, pause this and practice those before you continue. And lastly, in this section, we're going to review solubility of ionic compounds. So on the last table in your book, you talked about, it asked for states in there a little bit, but there's a note that says don't worry about states. You can go back now and you can answer those states once you've learned this for your ionic compounds. So some ionic compounds dissolve better than others. This is in your data book that you have. So make sure again that you've printed that off and you're using it throughout here. This is called a solubility table and it's only for ionic compounds. If you notice, the title even says ionic compounds. So this is going to tell you whether it's very soluble or only slightly soluble. Slightly soluble is going to mean that most of it stays as a solid, so we're going to give it its state S. And very soluble means that it breaks up into the two individual ions, and the ions are surrounded by water, therefore they are aqueous, AQ, for aqua, for aqueous. Okay, so the symbol S or AQ. Okay, I have 3 examples for us to try here. When you're looking up to see if I place this in water, is it going to mostly dissolve or mostly stay solid? The first thing I want to do is I want to look up the anion, the Br minus. So here is the Br minus column, and I'm going to just look at this column now. And in that column, I'm going to try to find the Na plus. So is the Na plus in here or is the Na plus in here? If the Na plus is in that top section, then it is very soluble. So we're going to call this aqueous. And if it's in the bottom section, only a tiny bit is going to dissolve. And so we're going to call it mostly solid. Okay, so it is Na plus is not one of these that's listed here with the silver ion and the lead ion. I'm not sure why my pen isn't working here. It's not one of these, and so it's going to be the top one. Okay, so the top one is mostly aqueous. So this is going to be aqueous. Okay, so let's try the next one. Again, I'm going to be looking up the anion, which is, now this is a polyatomic ion, so it's all of those. So you have to be comfortable with the fact that that is my cation and this is my anion on this ionic compound. Remember, you only ever have one of each. You only ever have one cation and one anion. So I'm going to look up this anion up at the top. So I find it here. Now, by the way, if there is an example that's given to you on a worksheet and it's not up here, you're not expected to memorize it or to know it off by heart. It's just that that sheet was designed with a different table that from a different teacher. So if you can't find it on the table, don't worry about it. It would just put like omit or exclude. It would not be on a test at all, okay? Okay, it's just that you can't always make sure that every example matches the exact solubility table for that particular teacher, right? So it's okay. Reach out to your teacher if you're not sure if that's something you should know. Okay, so first of all, I found this anion here, and now I'm going to look for the cation cesium. So would the cation fit here or fit here? Well, none are only slightly soluble. That would be a solid. All are very soluble. So this would be an aqueous state. Okay, let's look up that last one, that carbonate and the magnesium. So I'm going to look up the carbonate first up at the top, and I'm going to find it right at the back at the last column here, and I'm looking for the carbonate matched with one of these things. Now the carbonate is only soluble, highly soluble aqueous with group 1 or ammonia, so which is also 1+. So all these 1+. Magnesium is in group 2. It's in the second column. It's magnesium 2+, and therefore it's going to fit down here with the most. So this is only going to be slightly soluble, and therefore we're going to call it a solid. Okay, again, spend 10 minutes practicing the rest of those on your sheet.